So first of all, thank you for coming to the talk. It will be a different talk, but you'll see some overlap between the first one. This is joint with Pete Troyan, who's at University of Virginia. So how do I advance? Is this
the arrow keys out? Okay, yeah, you should be good.
Perfect. All right, so this is the basic question I'm interested in, is how should we rank colleges? And to be honest, what I'm really interested in is how should we rank academic journals, okay? But, you know, a topic that's near to our hearts. So I want to settle for once and all, is JET or TE the better journal? Okay? So, you know, we could just talk amongst ourselves. All of us have an opinion about the journal rankings. All of us have an opinion about the college rankings, and we could just try to figure out some way of aggregating preferences. And of course, we don't want to do this, right? Because this is just Era's world, and we know this leads to impossibility results. So what makes this different, what sort of gives hope and what's going to lead to possibility results, is that the ranking of colleges, the ranking of journal articles, is the outcome of a competitive process. So it's not passive. And so the key here is that both these, in all these applications, the object we're trying to aggregate preferences over selects the participants. So the way I like to think about this is, Era's world, we have too much information, and we need to come up with a filter that sort of, which of these rankings are we going to use, and which of these rankings are we going to ignore? And this is going to be the key that leads us to some possibility results. Did you touch something that I can't? Sorry.
We lost the slides again, I think.
Okay. So it's basically a standard arrows problem with the key difference is that we have an assignment, which is hopefully resulting from a selective competitive process. And the more competitive, the more the selection, basically the closer to stability, the more our approach will make sense. Okay? One key point here is that I'm going to assume the objects have unit capacity, and this is just going to make the characterizations really nice. Okay? So there's basically two different approaches. The one that's super common, that we're all familiar is what I'll call a regression. A regression-based approach, which is that we identify a couple of proxies for qualities, things we think are correlated, and run, you know, like however they do it, regressions on these. So these are in journals. This would be acceptance rates, citations. For colleges, this would be things like admissions rate. So this is common, right? And I don't think, so you talk to any academic, none of us like these rankings. I don't know any academic who likes rankings, these regression ranked approaches to ranking journals. And it's very predictable. This is a good example of Goodhart's law, which is that once a measure becomes a target, it ceases to be a good measure. Any ranking that's used, US News and World Report, that we know what they input, and so schools try to game the admissions rate, try to game yield rates, journals, of course, both citations and acceptance rates. So there's another interesting one, which is closer to like the tournament selection that we've seen, which is revealed preference. This is how they rank people. Sort of the rough approach that they used in this nice paper was to construct each student at a college as a tournament. They're choosing between different schools, and they select one amongst the ones they got into, and they're going to treat this as a tournament, and then we're going to aggregate rankings like you would do for chess or tennis. Okay? So we're going to propose a third alternative, which is what we call an approach based on desire. Okay? So here's my little hokey diagram, but so desire is we're going to be looking at the upper contour set. So I want to look at colleges that you prefer to the one you're going to, or journals that you prefer to the one you got accepted to. Revealed preference looks at the opposite direction. Now, economists, we typically look at revealed preferences as the basis for many different things, but it's not really clear why. I think it's from historical data, that people had observations about what you bought and price information, and so you could infer what you could afford, but you couldn't infer what's in the upper contour sets. But interestingly, for many of the applications that we're interested in, it's exactly the opposite. We can see what you're rejected from, but not where you would have sent. If your paper gets into JET, I can see potentially if it was rejected from Econometrica, but I never know what's the next journal you would have sent. So it's not really clear why we're always looking at revealed preference, and I'm going to argue there's a couple different reasons why desire is actually better. Right? So here's the example I like to give. So Al Roth moves from Harvard to Stanford, and the Stanford people are all excited, right? This is evidence that Stanford is better than Harvard, right? We have revealed preference. Okay? So we chose these because both these people were on Pete's committee. But Fujito moves to Stanford to University of Tokyo, and now maybe Stanford's not quite so happy with the revealed preference inference, right? Now we would infer that Tokyo is better than both Stanford and Harvard, right? And so what's going on here is that the revealed preference is picking up on the idiosyncratic component of a person's preferences. So idiosyncratic, unusual, means somebody has a reason for preferring, in some sense, the inferior person. And what happens is that they're going to be accepted by that school in the selection process. So the distinction between desire and revealed preference, so when is University of Tokyo going to be ranked higher based on desire? It's when professors from Stanford want to move to Tokyo but are not able to. Tokyo doesn't want them. Then the Stanford professors would desire Tokyo because they prefer it to their outcome. Revealed preference is instead making this inference as soon as a Stanford professor wants to move and is able to move. So it's a subtle distinction, but the reason, so we can talk offline, the reason why we think it's a little bit better is it's going to avoid the idiosyncratic component of the preferences. Okay? So I apologize, I've got young kids, but my axioms so sound like nursery rhymes for 6-year-olds. But our axiom desire is a school you desire should be ranked higher. Okay? Actual axiom is more technical than this, but it's also strictly weaker than this. And so from a characterization standpoint, it's preferable. So second condition, so we're going to have some schools ranked higher, we're going to have some schools ranked the same. And you think about it, ranking 2 schools the same is a very, very strong condition. All right, so we're saying there's no difference between these 2 schools. And so I just want to ask a thought question. I want to ask these students attending these schools, well, which one do you think is the best? And if there's one school that's over-demanded, lots of students in that class think it's the best, well, you can also see by balance there'll be one school that's under-demanded, nobody thinks that that's the best in that class, then I'm just going to reject the notion that these schools are equal. Right? I'll just say, in order to say that these schools are truly equal, I'm going to impose a balance condition on these conditions. So we'll say an assignment is perfect if every student can be assigned her favorite school. And so our balance axiom is that if we restrict attention to an indifference class, so just schools that are ranked exactly the same, that there should be a perfect assignment amongst the students who are at this school. Notice that, so what we want really is a strict ranking, and this is trivially satisfied in any strict ranking because. All right, so our last axiom is sort of based like how do we distinguish? We want a reason for why a school is ranked ahead of another one. And so this is kind of based on this notion of an under-demanded school. Under-demanded school is a school that nobody wants. And so I want under-demanded schools to be ranked last, right? And so the axiom actually we're going to use is just a recursive version of this, but it's fine to think of this. If school nobody desires should be ranked last. Okay? So unlike arrow, so we have, so we're going to get a nice possibility result. So not only are there ways of rankings that satisfy these conditions, but we're actually going to get a unique ranking that satisfies these 3 axioms. So it's a unique ranking that satisfies desire, balance, and justified. I'm going to try to give, well, I'll explain what the ranking is, but then try to give some intuition for why we get the uniqueness here. Okay? So the foundation of this ranking is starting with the last ranked schools. So again, I want to identify sort of schools that are under-demanded, not desired by any student. Now, unfortunately, these might not exist. There's sort of a fun fact, there always exists an under-demanded school for the male optimal stable assignment, but that's unique to that assignment. It's not true even for stable assignments. So we're going to try to generalize this. Okay? So what I need, so the last ranked schools, they're not desired by anybody, and there's a perfect assignment when I restrict attention to this. So I'm going to call this isolated perfectly. So I'm going to say a set of schools is isolated perfectly if nobody outside that set wants any of the schools in the set. Again, this is what we're thinking about as the last ranked schools. And the perfect says that, so they're isolated, but if we restrict attention just unto them, there exists a perfect assignment on that subset. Okay? So a couple things to notice. First of all, the empty set is trivially isolated perfectly. But also, if there exists an under-demanded school, the under-demanded school itself will be isolated perfectly. But not only that, the set of under-demanded schools will be isolated perfectly. Nobody wants those schools, and they don't want the other schools because those schools are under-demanded. And so there exists a perfect assignment. Okay? So I'm a sucker for lattice results and pigeonhole results, and so we actually have a nice one of both, okay? So, which is to say that the union of two IP sets is going to be an IP set, as is the intersection. And it's such a short and fun proof that I want to do it, okay? But the main point for us is that this is how we're getting this unique ranking, because an immediate corollary means there's a unique maximum IP set, okay? And so here's the argument. So take a student that's outside, so we've got A and we've got B, and we're looking at the intersection and the union, and we're trying to figure out it exists, are they isolated, does it exist a perfect assignment, okay? So start with a student who is not in set B, so it's in A, not B. Well, B is isolated perfectly, so that means I is not in B, that means I doesn't want any school in B. So if we ask I, what's your favorite school, I don't know what it is, but I know he's not pointing to any school that's in the set B, because B is isolated. A is also isolated, so any set in the B not A is not going to point to anything in A. And we look at the intersection, now we have a nice, real simple pigeonhole argument. If something in the intersection pointed outside of the intersection, well then necessarily some object would be pointed at twice, and that would mean something in the intersection is not pointed at all. And so there wouldn't exist and this is just restricting on the set A, so there wouldn't exist a perfect assignment. And so we have this nice decomposition of everybody has to be pointing in the right areas, and that implies that we're going to get this nice lattice result, the union in the intersection. Okay? And this is really the foundation. So once we can identify the maximum isolated perfectly set, this has to be the set that's of schools that's ranked last. Okay? All right, so how do we do this? So I call this delayed trading cycles, and you'll see why in a little bit. So we start with an assignment, and so there doesn't have to exist a non-trivial IP set, but any Pareto efficient assignment does. And so what we're going to do is we're going to use this sort of related assignment, which is we're just going to run top trading cycles, because now this is perfectly Shapley scarf world, where we have a student and an assignment, and we can run top trading cycles. We identify the unique maximum IP set. These schools we're going to rank last, and then we're going to remove it and repeat. Right? So basically, this is a result on how we order the cycles when we're running top trading cycles. So this is, I think, easiest to see graphically. So each node here represents a top trading cycle in the normal process. So we identify the top trading cycles in the top, we remove them and repeat. But I'm imposing a condition so that you've got the cycles of students, and I'm going to have an arrow from one cycle to another if anybody in that cycle desires any of the schools in the cycle that we've removed. Right? So I'm kind of condensing a lot of information here. But what the maximum IP set is it's just the set of nodes here that are not being pointed at. So these are the set of cycles that are isolated. Nobody's pointing to them. Nobody desires them. And it's isolated perfectly because it consists of these trading cycles. So we ask these people, what's your favorite? And we have a perfect assignment within this set. And so we can push this set to the bottom, rank these students last, identify the next set of maximum IP set, and repeat. And this is how we end up with our process. Okay? So this is going to be the unique ranking that satisfies those three axioms. It's the unique ranking is going to satisfy desire, the balancedness, and the justification. Okay? So it's actually a really simple proof to explain why it's unique. And so let me run through the intuition behind this. So it's an inductive argument. Suppose the first k-1 steps that we've ranked people have all been according to these sort of top trading cycles. And now we consider the remaining, say, everything that remains, so the schools that we've ranked K or lower. Okay? So take one of these colleges. It's ranked K. This college has a student attending that college. It's a Kth ranked student. It's attending a Kth ranked college. And I just asked the student, what's your favorite remaining school? Well, this is a school they desire. They prefer it to the college they're attending. So the axiom of desire tells us that it has to be ranked at least K. But we've already removed the k-1 schools, so this tells us it has to be ranked K. So this college that I1 points to has to be a K-ranked college. It points to its own student who continues to point, and so we have to cycle, and what we might be worried about is that if we don't cycle back to the original vertex. But now you can see if we cycle to an intermediate step, we have a college that's being pointed at by two different students, and this is going to violate perfection. And so that tells us that within these rankings, that in order to satisfy desire and this balanced axiom, we have to have top trading cycles. So basically, the workhorse here is that desire and balance are giving us that the partitions, the ranking way where partitions have to consist of trading cycles. And then this justification is indicating to us that from the bottom, we have to have these maximum IP sets. And so you combine these two things, and we get a unique ranking that can satisfy these things. Okay? So basically out of time, but one question people typically ask is I'm assuming complete information. How much information do we actually need? And you can see we really, well, first of all, we're condensing a lot of information here. We don't need all the rankings. And we don't need all this sort of revealed preference. We don't need the last ranked schools to reveal that they prefer the best ranked schools. And so what we would need are these red edges. Remove this. And so it's not that we do need some information along the way, of course, but it's very much the case that we don't need complete information. Okay? All right, so the basic conclusion is we've introduced a new ranking system based on desire, and it's awesome. This is how we should be ranking journals. Right? Right?
All right, let's thank Thayer.
Right. Thanks.
And if there's any questions, either remotely or physically, I mean, physically, Thayer can take them, but just repeat the question after for the virtual audience. Thank you.
Perfect.
So I think I may have missed this. What happens when you have a cycle, and so there's some set of students such that there's a loop among colleges?
Yeah, so then they'll be ranked the same.
They're all ranked the same, and so that's when you stop if there are all of them.
Yeah, I think yours is the best. You think mine is the best. And so first of all,
Could you repeat the question? Sorry.
sorry. I already forgot. When we have a cycle amongst the colleges, what happens? Right? And so here this will be, so I would say that we don't have any information to distinguish between these. And so the first thing to recognize is this implies Pareto inefficiency. And the second thing is that what Pareto inefficiency is applying is that the difference in where you're going is based on the selection process, not based upon your preferences. And so by the preferences that we can't distinguish. One thing that's sort of interesting is that you might have this intuition that this leads to this big mass of schools that are all ranked the same. And that's not the case. And the reason why is because this balanced axiom is actually a really strong condition. You can see if we we can show that as the market goes large, for any percentage of the market, it's got to vanish. And it's because you can't have a perfect assignment over 10% of the market when people have those discrepancies. So we will have some indifference, but that balanced axiom is actually going to basically provide our discipline so it doesn't get out of control. Questions?
You mentioned this result right at the end, that you don't need to see all of the edges to be able to. Do you have anything quantitative on that? Like in the worst case, how many edges do you need to be able to see?
Yeah, so we get this. So sorry. The question is, do we have any like sort of actual results, quantitative results on like how much information do we need? Short answer is no. But you can also see because we would have to embed that in a further model, right? So which is sort of the notion. Intuitively, because again, we're going to have these small indifference classes, and so if you kind of think of a continuum of different quality levels and we have small ones, we just really need information to distinguish between up and down. And so we don't, the short answer is, so I need people like me to distinguish between NC State and Virginia Tech. I don't need me to tell you that Harvard is better than NC State. And so it's really, the nice thing is it's the relevant set of schools, the relative journals that, I don't need actually somebody submitting to the International Journal of Game Theory to first submit to Econometrica. I just need, when you're trying to distinguish between JET and Econometrica, that you first submit to the one versus the other. So that's a dodge. The short answer is no, I don't have any.
But for the ones that are the same, it's trickier, right? Because you need to see the actual.
Yep, for sure. Any questions?